Hi. So we're going to look at something called Hess's law. Kind of Hess's law of summation. And basically, the idea behind Hess's law is that it's a state function. So it doesn't matter does it mean to be a state function. It means it doesn't matter how you get from point A to point B, how you get from reactants to products. What matters, it doesn't matter how you went from here to here. Analogy, it doesn't matter how you went from home to school. You may have left your house and ended up at school. Okay. Or you may have left your house. You may have gone to Dunkin' Donuts. You may have gone to your friend's house. You may have gone to McDonald's. You may have gone back to your house to get your homework, and then you went to school. Okay. What matters is you started at home and you ended up at school. It doesn't matter how you get here. And home is the reactants. This is what we start with. And school is the products. This is what we end with. So Hess's law, a state function, works on the idea that, or function is based on the idea that it doesn't matter how we got from reactants to products. What matters is these are the reactants and these are the products. Okay. A couple of background pieces of information I'm going to tell you as we get started here, and I do need to share my screen. Is a couple things about what's going to happen here is you are going to be provided a series of thermochemical equations, right? An equation with an enthalpy attached to it. And you're going to take those equations and you're going to manipulate them so that the overall equation, and I'll show you what I'm talking about, has the same reactants to products as your target equation. Okay, so let's look at what happens when you do the manipulation that is required. All right, there we go. If a reaction is reversed, then the sign of delta H is reversed, right? Positive becomes negative, negative becomes positive. If a reaction is multiplied or divided by a number, then the same happens to the delta H. All right, and let me just, the easiest way is just to jump right on in. So let's look at the example problems that we have provided. And here is the first one. All right, so this I would call our target equation. And we are asked to calculate the delta H for this equation. So essentially we need to know delta H equals question mark. We're going to utilize Hess's law, where we're going to take the three given equations and we're going to manipulate them, multiplying by numbers, divided by numbers, reverse them so that the products become the reactants and the reactants become the products, such that when we simplify what we will be left with our target equation. So the first thing I'm going to do is I'm going to go to my target equation and I'm going to look at the first substance, and that is ammonia gas. There are 4 ammonia gases reacting. So I'm going to look at the equations provided to me. I'm going to find the one that has ammonia gas, and I'm going to manipulate it so that I have the appropriate numbers of ammonias on the appropriate side of the reaction. So I need 4. I have 2, so I will need to multiply this by 2. I have 4 reacting. This has 2 produced, so I will need to reverse. So I'm going to times it by 2 and reverse. So let's rewrite that, okay? Over here, let's rewrite it to where it's times 2 and it's flipped so that I now have 4 NH3 gases. producing 2 nitrogen gases and 6 hydrogen gases. I will need to get my new delta H because it was flipped. It's no longer negative, it's positive. And because it was multiplied by 2, it's 91.8 times 2. We should be able to do that in our head. 183.6. And that is positive. And that is kilojoules for this reaction as written. Okay. Now I go to my next substance in my target equation. But I go down and I'm like, well, here's oxygen. And look, here's oxygen's too. So which one of these should I use? And I'm going to tell you that that's my hint that I'm just going to move on to the next species. And I'm going to let my oxygens work themselves out. So let's go ahead and just look at NO. Because NO is only in one place. So this must be used to figure out our NO, all right? And what I see is I need 4 nitrogen monoxides produced. This reaction gives me 2 produced, so I will need to multiply this by 2, but I do not need to flip it. So let's rewrite that, and we end up with 2N2 gas plus 2O2 gas yields 4NO gas, okay? And my delta H for that is still negative 180.5, but it is multiplied by 2 because we have 2 of those reactions. So it's now negative 361 kilojoules, okay? I will now go to my target equation and I will look at my next species. That is 6 water vapors produced. Now I've already used this equation. I will not use it again. I've already used this equation. I won't use it again. So my waters will be these waters. I need 6 produced. This provides 2 produced. It will need to be multiplied by 3, but not reversed. So that will give me 6H2 gas plus 3O2 gas yields 6H2O gas. And the delta H for that process is negative 483.6 times 3 equals, and that is 1,450.8 kilojoules. Now let's look at this equation. All right, let's ensure that when we simplify these 3 equations, we get our target equation, okay? So what we're going to do is start adding reactants that are similar, adding any products that are similar, or canceling any reactants and products that are similar. What do I mean by that? I mean that right here I have 2 nitrogen gases produced, and over here I have 2 nitrogen gases reacting. So those will cancel. Do you see anything else that will cancel? I do. I see 6 hydrogen gases produced and 6 hydrogen gases reacting, so those will cancel. I also see that I have 2 oxygens reacting and 3 oxygens reacting, so those will not cancel, those will add together. So overall, I've got the 4 NH3 gases plus the 5 oxygen gases yields the 4 NO nitrogen monoxide gases and the 6 water vapors. And the delta H should be the sum of all of these. So that's 183.6 plus negative 361 plus 1450 point. Oh, that's a negative right there. Right? Look up here. That's negative. Ooh, hopefully y'all already saw that. I was waiting to see if I would get it. Negative 1450.8 equals, and I have negative 1,628.2. I did not pay attention to significant figures. Kilojoules. I don't know if the answers are provided here. They're not, so I don't have a way to check that. But that to me makes sense because we are combusting. Oxygen is a reactant, and typically that's going to release energy, and that's what we have here. Now I'm going to leave these two here for you to do. You do not need to do this, okay? You do not need to do this. Okay. Oh, that's a great problem. So those would be fun to do. But I would like for you to look at 2 and 3. Okay? Right on, guys. Just take your time, one step at a time. You're doing great work.